All right, so in this example, we're going to kind of review a little bit of the stuff from chapter 3 and then also kind of check the conditions for inference that is new. Some people believe sitting closer to the front of the classroom will increase their learning and therefore increase their performance on assessments. For a unit in math, 30 students were randomly assigned to 7 different rows, and their score was recorded on the unit test. So we can see row 1, 2, 3, 4, 5, 6, 7. Okay? And if you want to type this in your calculator, you can. I've already got it in my calculator, row and grade. Find and interpret the correlation. So that's the R value, the correlation coefficient. So on the calculator to get that, we're going to create a scatter plot. I want to use row to predict a student's grade. Let's do the regression analysis. Let's do a linear model. Looks like a linear model is appropriate. Not a real strong relationship, a lot of variability there, but it does look like it's got a little bit of a negative slope, I guess. When you run the regression model, it stores that correlation coefficient in your calculator. If you go to the vars key, stat R, there's a correlation coefficient. So negative 0.184. Interpret. A lot of kids get this wrong because they think they need to interpret the actual number. To interpret the correlation coefficient, we just do the DUFs, right? We describe the relationships, direction, form, strength, and if there's any unusual features. So I'm going to say there is a very weak negative linear relation. So there is I'll just say weak negative linear association between row and score. For the people in this experiment, type of something like that maybe. All right, check the conditions. So we're going to do the liner. So L, linear. Look linear, didn't it? We could also analyze the scatter residual plot if you wanted to. Analyze residual plot. The residual plot shows random scatter. So I'm going to draw a little quick picture of the residual plot. I don't want to. I should do a better job copying that down. If this is the AP test, we'd do a better job copying it down. The residual plot has no pattern. Check. Independence. 1. Each kid's score is independent of others' scores. I guess what we'd be checking here is make sure kids aren't cheating off each other. You know, each kid's score is independent of what everyone else is doing. Second portion of this check is the 10% condition, which we will not check because this is an experiment. We actually aren't sampling at all here, so we don't check the 10% condition. We assign these kids to these places, so we're going to say that passes. Liner N for normal. So what needs to be normal? Well, what we need to look at is the plot of the residuals. Not the residual plot, but a one-dimensional, a univariate graph of the residual list. When I did the regression analysis, it stored the residuals into stat resid. So there's my residual list. I'm looking for symmetry with no outliers. Residuals are approximately symmetric with no outliers. So I'm going to copy the graph down here. Resid plot. This was row versus resid. copy it down a little bit, try to get it accurate a little bit. So I'm going to say checks, and I'm going to say residuals are symmetric with no outliers. So checks. E equals standard deviation. So what I'm looking at here is I'm looking at either the original scatter plot. I'm looking to see if these values are approximately equally distributed for all values of rho. And I can see it from both the residual plot and so I'm going to comment on the residual plot here. The residuals are equally spread about y equals 0 for all rho values. I'm commenting on this graph right here. Okay. Last one, random. Remember, this is an experiment, so don't say random sample. Rows were randomly assigned to the subjects. So, the conditions all check out. Find the least squares regression line, use proper notation. So I guess I just got to copy down this 85.3, negative 0.926. So my predicted score is 85.3 minus 0.926. Did I get that right? 926 times your row number. Interpret the slope. What does this value mean? Slope is negative 0.926. That's change in y. Change in y is your score. So that's going to be points per row. Every one row you increase in order, and every one row you move back, your predicted points are going to decrease by about 0.9. So I'm wondering if I should put down the when using a linear model with blah, 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 you know, kind of like that can statement to set up our model. Not so sure it's needed here. I'm just going to interpret the slope. For every one row a kid moves back, their predicted, very important that you put the word predicted here, their predicted score decreases by 0.93 points on average. These are being a little redundant, having both of these predicted, but it's all right. Y-intercept. So this means if your row is 0, then your predicted score will be this. Row is 0, I guess that means you're sitting like you're on top of the teacher or something, or like right face right on the board or something, I don't know. If a student sat at row 0, their predicted score would be 85.3 points. Now, doesn't have a whole lot of meaning because you can't sit at row 0, but you get the idea. Find the standard deviation of the residuals. So this is something we struggled with a little bit in chapter 3, because when you run that regression analysis, it does not calculate the standard deviation of the residuals. In fact, if you remember in chapter 3, I taught you to go to Menu, Statistics, Stat Tests, and had you run a linear regression t-test. Now at the time we didn't know what that was. We're actually going to learn what that is today or next video or something. And if you put in your row and you put in your grade, leave the rest alone, one of the outputs is the standard deviation of the residuals. 9.9, I'm just going to say 9.9. So S sub E is equal to 9. What was it? 9.9. 9.9. Didn't ask me to interpret that. That's all right. I think we interpreted it before. Find and interpret the standard error of B. So whenever we ran this right here, we also see the standard error of the slope. So that's a new value for us, 0.93 or 0.93. So the standard error of your sample slope is 0.93. By the way, just to cycle back here on one of those formulas we didn't need to use, they calculate it using this formula right here. Okay? So we don't have to know how to calculate it. We're just going to get it from computer output. And we need to know how to interpret it. Standard error of the slope. That is the spread of the sampling distribution of my sample slopes. Got all these little sample slopes here, right? The true population slope is beta, and it should be at the mean, assuming we took a good, simple random sample and all that good stuff, right? So what this is telling us is, when we take our sample slopes, our sample slope is going to typically be this many units away from the true population slope. So, when repeating this experiment, because this wasn't a sampling tick thing, I want to say sample slopes, but I guess we should be calling them experimental slopes. I'm going to still say sample slopes. I don't think that's going to hurt us too bad. Our sample slopes, or our experimental slopes, will typically be 0.93 points per row away from the true population slopes. I'm not going to say true population, but the true slope. The true slope. What would the true slope be? The true slope would be like if you took all kids, like the kids in this study, and randomly assigned them to the rows and repeated this thing over and over and over and over and over again millions of times. The true slope would be the slope of all that census information. So our sample slopes, our experimental slopes with our little group of, 30 kids, we repeated that over and over again. Our experimental slopes will be that many units away from the true slope. Describe the sampling distribution of sample slopes. Well, this is kind of a silly question. It's going to be centered about the mean of my sample slopes is going to be beta. However, I don't know what this is, so I can't really say what that is. The spread, because the conditions for inference are met, the standard deviation of B can be approximated with the standard error of B, which is 0.93 points per row. And the shape is going to be approximately normal because the conditions for inference were met. Okay? And now I know about this. Now I know what that thing looks like, the sample slopes look like. Now I can set up confidence intervals and hypothesis tests for slopes.